Hello, everyone. My name is Roberto SCHAEFFER. I'm going to be sharing this section here now. The focus now is going to be more national. In fact, all three presentations are related to Brazil, one more related to deforestation, the other one more on agricultural residues, and the third one on agriculture. So let me start by inviting Geanderson AMBRÓSIO from PIC to make the first presentation.
Okay, so my name is Geanderson AMBRÓSIO. I'm currently working at Utrecht University and also PBL in the Netherlands, but this work is from my time at PIC. I was completing my doctorate back there in 2019, and this work is dated from back then. So a little bit of content here. As usual, I will start with an introduction, and then I will describe the methods, some results and conclusions, takeaways, messages. So as an introduction, I would like to emphasize the environmental and agricultural relevance of South America. South America hosts 5 biodiversity hotspots. 2 of them are in Brazil, which are Cerrado and Atlantic Forest, and 3 of them are on the west coast of South America. Tumbos, Chaco, Magdalena, the tropical Andes, and the Chilean rainfall, Valdivian forests. And these, besides these biodiversity hotspots, also the region harbors the Amazon rainforest, which is the world's largest tropical forest. And it's kind of in between these biodiversity hotspots. In terms of agricultural relevance, I would like to emphasize the importance of South America in terms of global exports. It represents 53% of the oil crops, 35% of the bovine meat, and 22.7% of the cereals at the global level. But 61% of Atlantic forest, 44% of Cerrado, and 14% of Brazilian Amazon have already been converted to agriculture. So it pictures a quite concerning description of how Brazil is dealing with its, how South America is dealing with its agricultural and environmental relevance. So in order to steer the agriculture in Brazil, agriculture and deforestation policies in Brazil, Brazil has some deforestation policies, and I will describe 3 of them for the 3 largest biomes. So the legal Amazon, which is the green area here, it has a specific policy which intends to reduce annual deforestation by 80% until 2020. Another biome is the Cerrado biome, which has another policy intended to reduce by 40% deforestation. And you can see that legal Amazon, which is in green, overlaps Cerrado in this area here. And for the modeling procedure, we just assume that the highest mitigation of deforestation. And we also have some policies for Atlantic forest, which is on the coast around here. And actually for the Atlantic forest, there is no deforestation allowed. And we have seen that since the couple decades ago, the forest land and natural land has been quite stable in this area, or decreasing at a smaller piece. So considering the relevance, the environmental and agricultural relevance of Brazil and its policies for legal Amazon and Cerrado, this is our research question. So how does the enforcement and maintenance of the deforestation reduction targets for legal Amazon and Cerrado affect deforestation and emission leakage effects elsewhere in Brazil and abroad? So we are looking for the Brazilian policies and their effects within the policy area, in other areas of Brazil, and also at the global level. So to do that, we start using MAGPIE 4 modeling framework. MAGPIE is an open source partial equilibrium model. It minimizes a goal cost function, and the minimization of this function takes into account some restrictions, and those could be food demand restrictions, and also other specific restrictions like implemented at the grid level, which is the way that we implement the policies for the deforestation policies for legal Amazon and Cerrado. The original setup of the model has 12 world regions and 200 clusters. Within these 12 world regions, there is one region called Latin America, and Brazil used to be part of it. But MAGPIE 4.0 also has this really nice feature because it has flexibility for regional and grid data, which means that we could change or use other world regions and a different cluster setup. And we took advantage of this feature to come up with MAGPIE Brazil. And in MAGPIE Brazil, instead of 12 world regions, we have 6 world regions. And instead of 200 clusters, we have 500 clusters. And we took this decision focusing on Brazil and on its commercial partners. This is a representation of the original MAGPIE setup, and you can see each color here represents one different region, and between parentheses you see the number of clusters. So you can see there is the 12 regions here and 200 clusters in total. And if I move to this figure, this is the MAGPIE Brazil setup, and people can observe that we have many more clusters in Brazil, and we also have less world regions, and we have this big world region called rest of the world. But for our research question, the dynamics occurring in the rest of the world are less significant than the dynamics occurring in, let's say, Europe, USA, rest of Latin America, and China. So MAGPIE Brazil has this quite famous figure already, and I will use this figure to explain how we set up our research. So first of all, we use 6 world regions. One of them is Brazil, which is separated from Latin America. We are using 500 clusters, explicitly focusing in Brazil again. We use SSP2 as driver for population GDP. And most interesting, for the deforestation policies, this is our setup. So for legal Amazon, we have to have 80% reduction in deforestation in 2020 compared to 2005, and policy starts in 2005, and then it follows a linear setup up to 2020 when it has to reach 80% decrease in deforestation. A similar approach is done for Cerrado, and the deforestation target is less strict here, only 40%. And as I told before, in the area where Cerrado overlaps legal Amazon, we remain with the legal Amazon mitigation because it's more restrictive. And we also reviewed all other policies in other countries' NDCs that state if a given country is intended to reduce deforestation, and we added this to the model as well. Regarding to the climate change effects, we use 2 RCPs. So in RCP 2.6, we do have carbon price, of course, and in RCP 6.0, we choose to not having carbon prices just because we wanted to have a scenario which is closer to the reality. So in the very end, our scenarios are RCP 6.0 with the Brazilian policy for legal Amazon and Cerrado, and RCP 6.0 without these policies, and RCP 2.6 with the Brazilian policies for legal Amazon and Cerrado, and RCP 2.6 without those policies. And we run MAGPIE from 1995 to 2050. And in this green area here, you can see the outcomes that I will be talking about. So I will be discussing about carbon, land conversion, forestry, pasture, land, and natural vegetation. So going for the results, I divided the results section in 3 parts, trying to divide them in 3 main messages. And the first message is that the Brazilian policy causes agricultural relocation from the policy area to Brazil and from Brazil to rest of Latin America. So the first aspect of leakage is actually agricultural relocation. So this is what we are looking for at first. So here we have we should be always comparing from the blue line to the red line. So it means from no policy to policy. And the results are in the upper row, we have 2.6, RCP 2.6, and in the lower row, RCP 6.0. And first, we will be looking on the results for Legal Amazon and Cerrado and compare it to the rest of Brazil. So what we can see, the blue line moves towards the red line, which means that cropland decreases in the policy area, which is expected, and then cropland increases outside the policy area in Brazil. Another similar result, now we look at Brazil and we look at rest of Latin America. Again, the policy results in decreased cropland in Brazil and increased cropland in Latin America, which is as expected. And here we have some maps showing how these changes occur. So in RCP, what I would like to highlight here is that in all those scenarios, we do see a change, an increase in cropland and food feed cropland share. And the figure actually shows the change in the share from 2005 to 2050. So the blue squares here, the blue dots, means that there is an increase in the share of food and feed cropland. And then going to pastureland, what we see similar results. So the policy decreases pastureland in the policy area, but in the very end of the time frame, we see just a similar result. So it's very important to take good care when evaluate because of the time frame. For instance, if one looks only to the end of the time frame, they could think that the policy has no effect, which is actually not true because it had some good effect in the beginning of the time frame.
Geanderson, 2 minutes to go, please.
Okay. And then we also have results for pastureland from Brazil to rest of Latin America. And now we have some mixed results. You can see that both lines, they go below and over here for Latin America, and similar happens here in the end of the time frame. And what we see is basically that in the deep Amazon, there is an increase in pastureland area, and it happens both in RCP 2.6 and RCP 6.0 in the absence of the policy. So this is what would happen in the absence of the policy. So the second group of results, now looking at leakage. So first, we do see that the policy increases the forest land area in legal Amazon and Cerrado and decreases its area outside, but still in Brazil. And looking from Brazil and to the rest of Latin America, again, the policy increases the forest land area in Brazil, but we do see some mixed effects for rest of Latin America. In RCP 2.6, we do have some incentive for afforestation, and it turns out that afforestation occurs in these areas. And in RCP 6.0, what we see is that forest land, in the case of the policy, we do not see much change over Amazon and just a small change in parts of Cerrado. But when it goes to the no policy scenario, what would have happened is that we would have lost all this forest land area in deep Amazon. And to finish, The policy reduces Brazilian emissions, but it increases emissions in the rest of Latin America and globally. So first, comparing the blue and red lines, the policy decreases global cumulative land use change CO2 emissions in Brazil in about 20 gigatons. But when we look at the rest of Latin America, it actually increases by 7 gigatons. And when we look at the world, there is about 1 gigaton increase. This is all in the RCP 6.0. But still looking at the world, we do see that there is some mixed effects over here. So we should take into account the time frame. And considering the RCP 2.6, we do have similar results. So the policy reduces the Brazilian emissions. It increases Latin America emissions, emissions from the rest of Latin America, and we do reduces global emissions a little bit. So to conclude, if it were not the mitigation policy for legal Amazon and Cerrado, the country would maintain its agricultural expansion over these areas as it did so far. So the policy, they do prevent, in the absence of the policy, we would have much more deforestation. However, agricultural relocation, liquid deforestation, and emissions should be accounted for when designing deforestation policies. So as we saw, different levels of policy evaluation are fundamental for better addressing these dynamics. So the policymakers should take into account the policy area and the area outside the policy area. And also the time frame matters, because depending on your time frame, you can say that the policy was successful or not. So that's it. Thank you, and sorry for being late.
I want to make a comment, Geanderson. My understanding is that you focus on policies and not on the, let's say, on the enforcement of those policies. Because what we really see in the case of Brazil is that deforestation is going up. Let's say land use is completely being changed in Brazil. Although the policies are in place, the enforcement does not is taking place. So this is my only comment, but I see Jonathan have a comment. Jonathan, you want to raise an issue, please?
Yeah, I was just on very interesting work, G. Did you also look into the effects on trade and how strongly this is affected?
Okay, we did look. I just choose not to present it here, but the effects are not too much. We did look at it. I just decided not to present. We do have other results for production, also for food price indexes, but due to time constraints, I just decided not to present. And yeah,
I think it would be a very interesting result also, right? Like if it's possible that Brazil just maintains its current status as an agricultural player, but does not need to do further for deforestation. That would be, I think, also a great message.
Yeah, one of our results was that we could achieve the same level of agricultural production even with the policy, or with or without the policy, we would achieve the same level of food production, because in the case of the policy scenarios, the model decides to increase productivity. So it meets the food demand anyways.
Yeah.
And just a comment to Roberto's first comment. We explicitly do not look on policy enforcement. So those are hypothetical scenarios. I should have highlighted that even more, because this is a really strong assumption on the what if scenarios. So we do not discuss how to implement those policies. We are just presenting here the consequences of achieving those deforestation targets in a minimization optimal scenario.
Thank you very much. We have to move on. So I want to ask Taísa now to have the floor. Taísa is going to focus on the issue of agricultural residues. So Taísa, you have the floor. Please, can you share your screen?
Hello, everyone. My name is Taísa. I am a doctoral student from COPPE and research at Cenergia lab. And today I will present the work we did in Brazilian integrated assessment about the energy use of agricultural residues. So agricultural residues are a widely available and extensively distributed resource. And Brazil is one of the largest agricultural producers in the world that has a significant energy potential for residues, but it's poorly used. So it's important to understand how the penetration of agricultural residues as a bioenergy resource can happen and how it can contribute to reduce greenhouse gas emissions from the Brazilian energy matrix. Because of that, this work focuses on improving the representation of agricultural residues generated in the field in the BLUES model in relation to supply, logistic, conversions, and uses. So here represents the methodology applied to represent the crop residues in the model, where first we calculated the amount of generated residues in each agricultural technology, and we divided the residues into three categories according to the physical-chemical characteristics. Then we calculated how much of residues could be collected for energy use, considering, for example, the productivity of crops and the sustainable removal factor. After that, we created a processing and the logistic chain for biomass, distinguishing the type of use and the categories according to the processing needs. For all uses, the cost of harvest, loading and unloading, storage, and milling were accounted for. And centralized use adds the cost of drying for wet straw and the transport cost for all biomasses that varies according to the distance. And for large-scale use, pelletizing is necessary because it is used as solid biomass to compete with other biomass sources in the model. Similar to crop residues, for livestock residues, the generation of daily manure for a type of animal was accounted for. This manure was characterized and considered an availability factor, but the logistic costs of this resource were not assigned, considering that the centralized use will occur close to sources with high availability of manure. About the technologies, for distributed and centralized use, we add new technologies. In distributed use, the energy can meet the energy demands of the agricultural sector itself. And woody residues can be applied to generate heat or electricity. Livestock residues and wet straw can be used to produce biogas, and straw can be applied to all these. In centralized use, raw straw can be used alone for biogas production or with livestock residues through anaerobic co-digestion. And this biogas can be used for electrical generation. That will be incorporated into the Brazilian grid. Or it can be purified to be used as biomethane that which replace natural gas. In this biogas upgrading, there is separation between methane and carbon dioxide, and the CO2 can be either emitted to the atmosphere or captured. From there, it can react with hydrogen and produce more biomethane through the methanation process, or it can be stored, which means that the agricultural residues can enable a CCS. And the large-scale technologies were already implemented in the model, and it serves mainly to produce advanced biofuels, but it can also serve to produce electricity and hydrogen. From this, it was possible to calculate the supply curves to understand the availability of bioenergy as a function of costs. In other words, we calculated how much of biomethane could be produced considering the same cost of natural gas and the LPG at city gate. We can see that it is possible to produce around 0.08 exjoule of biomethane in competitive natural gas costs, which is about 11% of Brazilian final consumption of natural gas in 2019, and enough to meet the natural gas demand of the Brazilian transport sector. And compared to LPG costs, which is more expensive, the energy potential of biomethane increased to 0.34 ex-joule, which is equivalent to entire current consumption of LPG in Brazil. And this shows that biomethane has an interesting competitive potential comparing with this resource. Nonetheless, this curve was made in the absence of energy demands. It only considered food demands, so there is only dispute for land use and not with other technologies. For this reason, we also carry out an integrated assessment to see the dynamic dispute of agricultural resource technologies against the others in different scenarios. In the business as usual scenario, the residues don't have much participation. The NDC scenario uses more bioenergy than the bulk scenario, but it still has a low participation on residues as a primary biomass source, while the 1.5 degree presents a more relevant participation of residues, as it's a scenario that prioritizes the intense decarbonization of the energy system, including the hard-to-abate sector. In this 1.5 degree scenario, there is a small distributed use given by the generation of electrical energy from biogas produced from swine manure, but the energy demand of this sector is also small. The centralized use is mainly using straw with manure in co-digestion to produce biomethane. And all this biomethane production is produced with carbon capture and storage technology, due to the possibility of producing a net negative gas. In this scenario, the biomethane production is 0.16 ex-joule, and the biomethane meets most of the demand of final gas, natural gas. This pits still have a small portion of natural gas consumption. And finally, most of the residues go to the large scale use and serve to produce mainly advanced biofuels associated with CCS, and they also contribute to alleviating the pressure of land use by offering biomass with needed to expand the agricultural frontier. As for concluding remarks, the agricultural residues have a relevant energetic potential that can play an important role in Brazil's decarbonization strategies, and also can contribute to negative emissions in Brazil. Besides that, agricultural residues are a distributed resource that can reduce the cost of fuel and gas logistics in the countryside of Brazil. But there is still challenges to increase the participation of agricultural residues in the Brazilian matrix. And that's it. Thank you so much for your attention.
Thank you very much, Taísa. We have time for a couple of questions here. Yes, Jonathan, please go ahead.
Thanks, very interesting. So I was wondering, you mentioned the sustainable level of residue takeaway on agriculture, right? I think, and I guess it has to do with that we need to have a certain amount of residue left on the land to maintain soil fertility, right? Is that just an assumption, or do you have additional data on that for Brazil? I'm very much wondering what current practice is in Brazil, and if there is indeed potential, or if there's actually risk of more competition with that kind of use of residues.
Sorry, you can speak a little slowly.
Sorry. So I was wondering about the residues that are left on the land to maintain soil fertility.
Yes, we are conservative to permit the only 30% to be removed. We used a literature to establish this number.
Yeah. So this is one number for all agriculture areas?
No, we considering the productivity of the model is divided into 7 classes of land use that considering the time travel and the distance to urban centers, large urban centers, and the productivity of the soil. So we differentiate these classes to the full class C is used to take the amount of residues that have to stay in the field.
Yeah.
And we use this amount and they use it for all classes to avoid removal more than you have.
Yeah.
And
Taísa, let me help here. Basically, the question raised by Jonathan is, I say, whether or not this 30% maximum residue that you can take out of the ground has been kept constant for all regions?
No.
Or you have used a single number of 30% as a maximum, or you have varied that number according to different typologies or regions,
So
etc.
this 30% is for class C. 7 class 1 is the default that we consider the 30%, and the others we Pedro.
Sorry, Jonathan.
Go ahead, Pedro.
Really interjecting as a translator here. We do have regional differences, and we have land cost categories in our model. We have 7 of them, and she only presented the one that is the average, and that affects, of course, across Brazil with productivity, and it relates to how much residue needs to stay for fertility issues and so forth. So it does change quite a lot by region and cost categories within our model. She only presented the average cost category that we used.
Cool. Oh, very interesting. Thanks.
Okay, thank you very much, Jonathan, for the question. Thank you, Pedro, and thank you, Taísa. Let's move to the next and final presentation. Is Gerd. Gerd, are you there? Yes, great.
Yeah.
Gerd, the floor is yours. Please go ahead.
Thank you, Roberto. Hello, everyone. My name is Gerd, and I will present this work that I have been developing with my colleagues at Cenergia. Only a brief contextualization. Until 2050, it is expected increase of global crop demand by 60 to 110% only for human consumption and livestock feed. But that not taking account the quantity of demanded for energy production from the agricultural sector. And some models suggest that the bioenergy and the biomaterials will be critical to reach the well below 2 degree scenarios. And how to produce this quantity of agricultural commodities without pressuring sensible biomes such as forests like Amazonia. And one of the answers could be the sustainable transition of agriculture. So, the improvement of the agricultural production practice, such as the agricultural intensification, is very important for increasing the productivity of the sector and global food security. However, it is important to have intensification associated with sustainable production systems that focus on productivity gains and reducing environmental and climate damage. And it is estimated that the technical potential of the agricultural production systems diversification is able to mitigate between 2.3 and 9.6 gigaton CO2 per year. But there is also another group of technologies that is important to highlight, which is the disruptive food production that associates a new way to produce food next to the consumers, using the urban and the peri-urban areas to produce food with high quality and without the levels of food losses, like vertical farms, urban agriculture, plant meat, culture meat, and others. And still, there is another group, more technological, like the utilization of enzymes to produce with less methane emissions in the agricultural sector, such as the rice with enzymes and cattle with enzymes. For that, we use the new Blues 2.0 model that was recently updated, which is a bottom-up and perfect foresight model. And Blues model is divided into 6 regions and has a time horizon from 2010 to 2065, considering time step of every 5 years. The Blues has 10 land covers and 5 agricultural technological classes fully developed, as well as a vast amount of agricultural technologies already implemented in the model. And we propose to implement another class, another group in the Blues model, that is the disruptive tech, enhancing the model, adding another class with a total of 6 agricultural technological classes. We already have these technologies in green that was already implemented in the Blues model, and we developed a new group of technologies that is in yellow. From these newly technologies, we verified all of the inputs like fertilizers, productivity, irrigations, emission, and other inputs. And after, we realized that is necessary to increase the number of technologies due to the variety of existing systems. So when there was a wide range of systems for each technology, we ended up developing 2 new. One with low inputs and other with high inputs. Okay. Hence, for the vertical farming, it was developed 2 systems: the low tech that represents a less energy intensive systems, and another that is more energy intensive, like black houses. For the urban agriculture, it was developed the urban gardens, that is less cost intensive, and the urban gardens. And the urban greenhouses, and the rice with enzymes. Okay. Then in the livestock, in the livestock, it was developed the intensive production of cattle milk with enzymes, mainly because a large part of the Brazilian dairy cattle is produced through the confinement systems, which allows the adequate feeding of the cattle with the enzymes. The planted meat was divided in soybean-based and other vegetables-based, like peas. Those imitating the 2 main brands of planted meats, the Impossible meats and the Beyond meats. And at last, the culture meat was divided in 2, first using cyanobacteria and other using soybean hydrolysis. And for this implementation, it was necessary to develop new technologies representing the entire food production chain, from the initial producer to the final consumer. This way, there was a more appropriate link between the different types of food production technologies with the demands and their respective levels of food waste, food losses through the production chain. Hence, we were able to close the entire cycle, considering the greatest losses arising from conventional agriculture production, with considered transport, storage, and industry, migrating to system with lower losses, such as community gardens, where the consumer lives really next to the producer. Okay. So it was developed 22 new agricultural technologies, all with links with the food chain of the Blues model. And only to try to show some results, you can see here that have only a small change between the old model and the new model with these new technologies, but only in climate scenarios like the 1.5 Celsius degree scenarios, with the reduction of the amount of areas used by the integrated system in contrast to a greater need to use areas intended for crops for the production of planted meats, for example. And we can observe that there was interesting penetration of disruptive technologies, especially considering the urban gardens and vertical farms, and a significant penetration of planted meat to try to replace the bovine meat. And to finish, the disruptive production systems are relevant for EAMs due to increase the mitigation possibilities. The scenarios has gained increasing importance in IPCC reports and publication from EAMs community as one with the largest GHG mitigation potential. So it's worth increasing the technology complexity of land use models to both represent the agriculture and the energy transition. And this includes the role of the agricultural disruptive technologies, because they can pave the way to a new and a more sustainable scenarios. And I appreciate the opportunity to be here today. If anyone has any questions, please feel free to get in contact with me by email or social media. And thank you very much.
Thank you very much, Gerd. Yes, Jonathan, please go ahead. Thanks for raising your hand.
Anyone else has a question, it's also very welcome, of course. Yeah, but very interesting work, Gerd. It's quite, well, I haven't heard about explicit inclusion of these, quite more uncommon, but maybe high potential technologies. That's quite impressive. But I was wondering, they're of course really expensive, made with possibly high emissions. And you showed some changes, but they were quite marginal in the end of the uptake. So what do you think? Is it really a solution to? Yeah, is it optimal in a way? Should we go there, or is it should we not?
Thank you, Jonathan, for your question. And it's a really important and interesting question, because I believe, I don't know if everyone believes that, but that could be a way, because nowadays we can see, for example, the beyond meat, the impossible meat, that penetrates really really well in our society. And this type of meat, the planted meat and the fermented meat that we are developing this technology is not very intensive in energy. So I believe this type of technologies is could be important to our models and to our society, and the urban gardens is really interesting too, because we can reduce the losses of the food chain. And here in Brazil, I don't know if everyone know, but the losses is really huge. So I believe that could reduce too much the emissions of the food chain.
Yeah.
But I think the cultured meat, it's a little bit more difficult to really implement, because it needs a lot of energy, and the quantity of energy is really huge.
Yeah.
So.
And I fully agree with the plant-based meats. It's very, very important, of course. Indeed, cultured meat a bit more difficult. But I was specifically also wondering about the vertical farming, and in the Netherlands we have lots of greenhouses, and they're extremely efficient. I mean, per hectare, it's really impressive production. But at the same time, the inputs they're crazy. I mean, the amount of energy, what it uses, and also other stuff. I think, for example, I think they even use peat, right, as a substrate for the plants to grow. So that's also the use of resources is really high. So I wonder if that's an efficient way.
Yeah, I agree totally. The vertical farms is really difficult, but the productivity per area is really absurd. So it's really big. So maybe in some countries, maybe that could be a way. But in Brazil, I don't know. I don't believe too much in vertical farms in Brazil, but maybe in Europe or in other countries that have small areas to produce the food, maybe.
Yeah.
Thank you. Before passing the floor to Geanderson, just to make a comment here, Jonathan. In fact, I think that most of the work Gerd is doing is very much methodological, in a sense, how to incorporate these new disruptive technologies in an integrated assessment models. So the focus was much more methodological than really try to grasp whether or not these technologies today will play an important role. But by being in the model itself, it greatly facilitates like what if scenarios to try to see what would be, let's say, the break-even point in terms of cost for some of these technologies to really become important. So I agree with you that some of the results he showed were quite disappointing, in a sense that, let's say, that it does not make that such a big difference. But the idea is really to have a methodological contribution on how to integrate that into AIAM. Geanderson, I think you have your hand raised. Please go ahead.
Thank you, Roberto. Also nice to hear your comments, because I'm about to comment in the methodological side as well. This is quite an impressive work that you have done, Gerd. So congratulations. And I'm wondering, have you did a research whether other IAMs or land use models have done such a, let's say, deep implementation of these high technological alternatives? And what would you say about other models that have done that, and how do your model compare to those?
Thank you, Geanderson, for your question. I tried to investigate some models if you have or not. But like you know, the models sometimes not really really explicit of all the models, all the technologies, everything. I know that have some people in PIC which developed some researchers in this context, including in next year I will go to PIC to try to develop these technologies in the COPPE model that is our global model. So I don't know if have any other model with have these technologies really implemented in the model, because our model they have a hard link with all the sectors. So we can observe, for example, the integrated systems if have or not something to aggregate with other sectors, for example, and the water sector and everything. But I really don't know if had or not.
Yeah, yeah. My comment was most because you did really quite a thorough job, so it was really well explained and implemented. And I haven't seen other IAMs or land use models with such a group of alternatives. Maybe Jonathan could say here some words because he knows better than I, but I haven't seen that. And definitely the first step would be, how would we be able to implement it in IAMs or land use models, let's say. And if you keep on going in this field, I believe that you can do great contributions.
Really good to know that, and that it's my DSC thesis. So I will try to develop everything in the COPPE, in the blues. So I expect to can do that in the COPPE model.